Hello, welcome to the 16th lecture of two-phase flow and heat transfer. Today we will be discussing about molecular dynamics. So, at the end of this lecture we will understand the following points. First, we will be understanding multiphase flow from molecular perspective. We will discuss the nature of van der Waals and columbic forces acting on the molecules. Then we will practice a case study based on molecular dynamics based freeware. There we will see how to install the freeware, how to set up the model parameters, how to run the case study, and finally the analysis of the results also we will be showing you over here. To start with, let us see where molecular dynamics lies in case of the scales of the problems. Okay. So, here you see I have presented a pictorial view of the scale of the problem in the abscissa and here time in ordinate. So, you can find out a very fast and low scale or small scale phenomena is being understood by quantum mechanics, whereas once you increase the length scale as well as increase the time scale, we can come to the molecular nature of the matter. And then once we move upwards, the extreme highest scale or engineering scale or extreme highest time or engineering time will be giving us the continuum mechanics what we see around. Okay. So, in between we are also having another concept which is called mesoscopic, which bridges the molecular nature to your continuum nature. There are different methodologies for continuum mechanics. This comes under the periphery of your computational fluid dynamics, but to name a few over here, we are having finite volume, finite element and finite difference methodology. In previous few lectures, I have shown you some mesoscopic technologies like smoothed particle hydrodynamics and lattice Boltzmann method like LBM. There are few more called DPD, dissipative particle dynamics also. Now, in this lecture we will be concentrating in this green block where we will be understanding the molecular features of the matter. Okay. So, what we will be doing, we will be trying to find out the properties or behavior of the matter based on the atomistic calculations as well as coarse grain molecular nature. Okay. So, this we will be finding out it is lying in the range of nanometers and the time level will be something around nanosecond to picosecond. Okay. So, let us see for doing a molecular dynamic simulation what things are necessary. So, here you see at the center I have shown you the molecular simulation model. Okay. And then it is supported by 4 parts over here actually. So, to set up a molecular simulation you need to do all these 4 features. To begin with, first you need to create the configuration and the topology. So, configuration and topology means with what type of molecular structure we will be starting our simulation, the fluid molecules we need to construct or the surface structures we need to construct. So, those will be coming over here, configuration and topology. Okay. Then we need to decide that what interatomic interactions we are considering. So, you know different molecules whenever they will be applying forces amongst themselves. So, there are different interatomic interactions, okay, whether that is columbic interaction, whether that is potential Lennard-Jones type of interaction. So, those things will be decided over here in this block where interactions will be actually finalized. Apart from that, we have to also give some sort of ensembles, that means we need to decide that which quantity we are actually going to fix up, whether it is number of the molecule, temperature of the molecule, pressure of the molecule. So, those will be decided in these ensembles. Also, we need to decide in this point what will be the method of integration. That means any computational fluid dynamic simulation we know that it advances with time, right. So, what will be the time advancement integrations that will be decided over here in this block. Apart from that, problem to problem we know that boundary conditions, pressure and temperature of the system, and if you are having some external influence like magnetic field or electric field. So, those things will be also need to be given in the simulation. Okay. So, all these 4 blocks will be coming into picture in case of a molecular simulation. So, let us see that what type of interatomic interactions you are having first. So, if you think about a very common fluid like water. So, here I have shown you water. You see this red colored molecule, red colored atom is actually your oxygen, and here we are having two hydrogens connected by the covalent bonds. Okay. Now, this water structure will be having fixed arm length for the OH bonds as well as fixed angle, okay, between two OH bonds. Okay. So, this is a common nature of the water molecule. Now, these water molecules will be doing multiple interatomic interactions. For example, one water molecule, if it is doing some sort of interaction with the another water molecule, so those will be called as non-bonded interaction, because those water molecules are not connected via bond. Okay. So, non-bonded interactions we will be finding out between two water molecules or two dissimilar or two non-connected molecules. Okay. So, there are various types of forces which will be applicable as non-bonded interactions. Few I have named over here. First one which will be applicable is called van der Waals force. So, between two molecules always will be having some sort of attraction or repulsions, that is guided by Lennard-Jones potential. Okay, Lennard-Jones potential comes out in this fashion. The potential U, okay, Lj symbolizes Lennard-Jones, will be actually summation of J not equals to I. That means J not equals to I means this will be not acting whenever we are considering interaction with the own molecule, okay, with the same molecule. So, J not equals to I means apart from this molecule, present molecule, all other molecules will be coming into consideration for this Lennard-Jones potential. Then we are having over here a nature of, you see, 4 into epsilon, then sigma by Rij, where Rij is actually the mutual distance between the molecules, to the power 12 minus sigma by Rij to the power 6. Okay. If you try to plot this U versus this Rij, so Uij versus Rij, this will look like something in this fashion. So, you see at very small distance between the molecules of interest, you will be finding out that the potential is very high. So, that means whenever the molecules are coming very close to each other, you will be finding out they are facing a very high negative repulsive force. Okay. And this goes to 0, almost 0 whenever they are very far away apart. Okay. So, this type of Lennard-Jones potential we apply as van der Waals force. Apart from that, if the molecules are charged in nature, then you will be finding out electrostatic interactions are also coming into place. So, that we use the Coulombic law of forces. So, electrostatic potential will be something around summation of once again J not equals to I Qi Qj by 4 pi epsilon naught Rij, where epsilon naught is the permittivity for the vacuum. Okay. And Qi and Qj are their respective charges stored in the molecules. Okay. Rij is their mutual distance. Apart from that, these non-bonded interactions, we can have also bonded interactions. I have already shown you that if we are having some covalent bonds in your molecular structure, then you will be finding out that they are supposed to keep some fixed length, okay, between the bonds, and then between the atoms in the bonds, and they will be keeping some angle between the bonds also. Now, it can be like this, that due to some external force or field, you will be finding out that these bonds are being stretched, or angles between the bonds are actually being twisted. So, there can be some torsional stress, or there can be some stretching stress also. So, depending on that, you may find out that whatever nominal r and theta needs to be maintained, that will not be maintained, and some other values will be coming. So, due to that, there will be some sort of torsional potential and stretching potential. So, the stretching potential can be written as U bond is equals to K bond. So, this is some constant we keep for different molecules. So, this is we are having some chemical charts from where you can get these potentials, constant for the potential R minus R naught. Here R naught is the what you can say equilibrium gap between the atoms in the bond, okay, square. Okay. Similarly, for torsion we can write down u angle is equals to k theta, theta minus theta naught whole square. Here also theta naught is the nominal angle in case of equilibrium, okay, between the bonds, okay, and k theta is once again constant, can be found out from chemical properties of the molecules. Okay. So, next let us see that apart from this, in the other block I have shown you that next we need to give the boundary conditions. So, here let us discuss about different boundary conditions available in molecular dynamics. So, first I will be showing you that we are having periodic boundary conditions. So, usually molecular dynamic simulations are done for a very small domain, because number of molecules will be high for a for simulation of one engineering problem. So, what we do, we squeeze the domain and consider that the domain is being repeated elsewhere. So, we need to keep a periodic boundary condition for this kind of simulation. Now, what does this periodic boundary condition means? Let us say here we are having a cell which is which we are considering for our simulation. So, what we will be doing over here, let us say one molecule is entering over here through this boundary. So, that molecule, whenever it will be entering, at the same time another molecule will be also going out from the opposite boundary. So, it is like this, from one boundary someone will be entering, from the opposite boundary same amount of mass of the molecules will be going out with equal velocity. Okay. So, this kind of things we call as periodic boundary condition, and this kind of boundary condition we apply very frequently for molecular dynamics. Apart from that, we also give some boundary conditions like fixed cell boundary. Now, fixed cell boundaries can be of multiple types. So, based on the amount of reflection, we divide it by two types, reflective and repulsive boundary condition. So, here I have given you example of reflective and repulsive boundary condition. Here you see reflective means it will be obeying all the laws of optical reflection. Okay. So, angle of incidence will be equals to angle of reflection, all these things it will be obeying. In case of repulsive, we will be finding out that it is getting some force, okay, from the wall. Whenever it is getting near to the wall, it will be getting some force, okay, so that it will not be colliding with the wall. So, let us say here we are having the wall, depending on the distance between the wall and the molecule, you will be finding out it is getting some potential. Okay. So, more the less the distance, then you will be finding out the potential is increasing. Okay. Apart from that, depending on the rigidity of the wall, this fixed cell boundary can be divided into two types, rigid and semi-rigid walls. So, here I have given one schematic of rigid and semi-rigid. So, here you see all these violet colored dots are actually wall molecules, and you can find out that due to motion of the inner molecules, none of the wall molecules are changing their position. So, this is an example of rigid wall. On the other hand, over here you see due to the motion of the inner molecules, the wall molecules are changing their shape. So, these violet colored dots are the initial conditions of the wall molecules, and the circular corresponding positions are actually the final positions of the wall molecule. So, you can see wall molecules are actually moving, okay, due to the interaction of the inner molecules. So, this is one example of some sort of semi-rigid wall. Okay. Though it will not allow the inner molecules to go outside through this boundary, wall boundary, but the wall boundary can deflect depending on the potential of the inner molecules. Okay, after discussing these boundary conditions, let us see the initial configuration and the topology, which is also very important for molecular dynamics, as I have mentioned. So, for deciding the topology, at the beginning we need to give whatever potentials and distances necessary for the molecule. So, here I have shown you a water molecule and silicon molecule, okay, for example, because majority of the electronic applications in two-phase flow, we place water droplet on silicon and do little bit of microfluidic applications. So, here I have shown you we basically use for water SPC/E model, okay, because many times we find out for microfluidic application electric field is very important. So, in those cases SPC/E, E symbolizes electric field, actually works well. So, let me tell you what are the characteristics of this SPC/E water model. So, what we do in case of SPC/E water model, we give the charge to the oxygen and hydrogen molecules. So, you see we give oxygen minus 0.8476 of multiplied by electron charge, and then in case of hydrogen we give plus 0.4238 multiplied by the electron charge. So, you see this QH is exactly half of the QO in magnitude and opposite in sign. So, this makes water as a whole neutral, and all the charges will be balanced. Next, what will be the bond length, that means R naught, and what will be the bond angle between HOH, that means the theta naught. Those values we set as 1 angstrom as R naught and 109.47 degree for theta naught. Similarly, for silicon molecule, what we do, we consider a diamond cubic structure like this diamond cubic structure, okay, and we decide the lattice constant will be 5.43 angstrom. So, between two silicon molecules we are having distance of 5.43 angstrom, okay, and usually for this type of applications we consider that the silicon is having no charge, okay. So, we give silicon atom charge is 0 into E, okay. Next, let us see that how we can place the initial configuration for simulation. Here I have shown you that we place these yellow colored particles are actually yellow colored molecules are actually your diamond cubic structure of your silicon molecules, okay, and over that we have created one water box. So, you can find out the red colored things over here, whatever you find out, those are actually your oxygen, and white colored atoms are actually hydrogen, okay. So, what we do initially for setting up a simulation, here I have given you one example of a water box over a silicon substrate. So, I have taken 15 cross 15 cross 15 matrix of the water molecules as a box over the silicon substrate, okay, and then initial distance between the water molecules we have kept as 4 angstrom. Remember, this is not the bond length or R naught, this is actually between two water molecules we have kept 4 angstrom, okay, and initial distance between the water and silicon surface is also kept as 4 angstrom. So, here this will be the figure for the initial placement, okay. Next, let us see what different ensembles and integration methodology we follow. There are various ensembling methodologies, amongst which I have named here 3. The first one is microcanonical ensemble. In this microcanonical ensemble, the number, volume and energy of the molecules will be being conserved, okay. Similarly, we are having approach like canonical ensemble, where number, volume and temperature, not energy, is being conserved. We are having isothermal isobaric ensemble also. Isothermal isobaric will be keeping number, pressure and temperature constant, okay. So, you can choose any of the ensembles. Next, if we see the governing equation, so we know that for particulate nature or molecular nature, it will be always boiling down to Newton's second law. So, if we write down Newton's second law for molecular structure I, molecule number I, so it will be Fi, the force acting on the molecule is actually mass of the molecule multiplied by the acceleration of the molecule, okay. So, from the potentials we can calculate what is the force acting on that in this fashion. So, Fi will be summation of all the potential, addition of all the potentials, non-bonded and bonded potentials, del R of that potential you can get as force, okay. Now, once we get the force, quickly I can find out what is the acceleration, okay, and using that acceleration we can find out the next position of the molecule. So, that we do using Verlet algorithm. So, Verlet algorithm already I have described to you, but let me give you one quick outlook over here. So, R of t plus delta t we can find out based on RT, Vt and At, okay. So, in this fashion, so Rt plus Vt into delta t, Vt is nothing but the velocity of the molecule at time t, half of At, which is the acceleration of the molecule at time t, multiplied by delta t square. In a similar fashion, Rt minus delta t, that means the previous time step, the history time step, is equals to Rt minus of Vt plus multiplied by delta t plus half of At into del t square. These are coming from your Taylor series expansion once again. Now, if you add these two, then you will be getting R of t plus delta t is equals to 2 into Rt minus of R into t minus delta t plus Ft by m into delta t square. Here intentionally what we have done, we have eliminated Vt, because Vt nowhere we are calculating, we are always finding out Ft. So, At has been actually replaced by Ft by m, okay. So, once we know the F, then quickly using this one and the previous knowledge of the positions of the molecule, we can find out the next position of the molecule. Next, let us see what are the different freewares available for doing simulation of molecular dynamics. There are few well established freewares like LAMMPS, GROMACS, NAMD, M-Dynamics, okay. But today I will be giving you an overview of LAMMPS simulation, okay. So, this is very robust software for molecular dynamics simulation. So, let us see how LAMMPS works. Now, to set up a molecular dynamic simulation in LAMMPS, we need to consider actually 3 different segments. So, first for fixing up the topology and initial configurations of the molecule, we need to go for a software called mole template. Then the whole molecular dynamic simulation is being done in LAMMPS, and finally for the visualization you can take any external software. Here I will be showing you the software called VMD, okay. First let me show you how to install LAMMPS, because this is very important. So, first what you need to do, you need to find out or you need to download the LAMMPS source code from the LAMMPS website that has been developed by Sandia National Lab, okay. So, you can download it as it is a freeware from there. So, before that you need to resolve some dependencies. So, dependencies I have written over here. So, those things you can resolve. After that it will be downloading as some tr.gz file. So, you need to enter that one. So, already I have shown you in the previous few lectures that how to enter a file, zipped file. So, you can enter that one. So, once you enter, it will be creating a directory like LAMMPS, then hyphen, and then the date will be coming. So, one example of the date structure I have shown you over here, 5 September 14. So, it can be changing depending on the date of download. Next, we need to go to stubs directory of this LAMMPS folder, whatever you have downloaded. The destination is like this, LAMMPS folder, then go to src, then in between that you will be getting a stubs directory. So, once you go to stubs directory by using cd, whatever I have told you earlier in Linux platform, then what you need to do, you need to first give the command as make clean and then make. Okay, so, it will be making your code, okay, ready for use. Then we need to install the software by going to the src directory. So, src directory is once again if you go one level up from the stubs directory, you can reach to src directory, and then there you type this command make clean all and then make serial. Now, make serial will be enabling you to run the codes in serial, okay. Here I have discussed the installation of the other software like VMD. So, VMD once again you can download from some website. So, the website ID I have given over here, this is freeware. So, first once again you have to unzip this one, because all the software will be actually in the zipped format to minimize the space. Then you need to configure, okay, the source file. So, configuring this one we need to give the, for configuring this one we need to give the command like this .configure Linux. Then you have to install by giving the command make install, okay. So, VMD will be installed. Similarly, mole template for the initial topology and configurations, you have to download the mole template from this website www.moletemplate.org. Then unzip it, okay, and set the path of the environmental variable, and you have to include this path using in your environmental variable export path equals to path colon dollar home, then home mole template slash src, okay. And at the end you set the mole template environmental variable also to common subdirectory by export mole template path home slash mole template slash common, okay. Next, let me go to the simulation methodology. So, first what we will be doing over here, I will be showing you that what we have done in mole template. So, this is a mole template file over here, main points I have highlighted. You see over here we have shown the oxygen, hydrogen and hydrogen, H1 and H2 are the 2 hydrogen atoms. So, first values are their charge 0.8476, 0.4238, 0.4238, and then next 3 positions are their locations x, y and z coordinates, okay. So, depending on the angular location 109.9 degree and their angular location 1 angstrom, angular length 1 angstrom, these coordinates can be calculated, okay. Then we have given the mass of the hydrogen and oxygen also. So, for oxygen we have given 15.9994 and for hydrogen we have given 1.008. We have also selected what will be the bonds and angles. So, bonds are selected between OH1, OH2 and the angle has been selected between OH1 and OH2. Okay. So, that angle will be theta naught. Okay, then we have specified that what will be the spring constants dependent on the LJ potential. So, here for OH we have considered that K R will be actually 1000 and R naught will be 1 and for the bond angle the angle will be 109.47 and K theta we have selected as 1000 once again. Okay. Now, for O and H the Lennard-Jones potential, that means sigma and epsilons are selected like this. Okay. In the next one I have shown you for silicon. So, once again you know that silicon is having a structure like this. So, you can always calculate by knowing the coordinate position of the silicon. So, here I have given the coordinate position. By the way, for charge we have given all zeros. So, first column you can see all are having 0 and their corresponding locations after that we have given. Here the silicon atomic mass we have given as 28.0855 and we have also set up that what will be the Lennard-Jones potential over here for the silicon 0.05 and 3.0. Okay. Then we have created a box of having 15 water molecules. So, 15 cross 15 cross 15 in each direction in this fashion. So, 15 and then we have given the initial position as 4, 0, 0 in x direction and then in y direction also 15 molecules. So, 0, 4, 4 and in z direction 0, 0, 4. So, it is a 15 cross 15 cross 15 box. Then we have moved the water box on a desired position to place it over the silicon substrate by some location. So, these are optional. So, you can give any value over there. And then we have set the domain size. You can see the domain size is starting from -50 to 200 for the x direction, 0 to 200 for the y direction and for the z direction, because z direction will be very high, we have to see the droplet dynamics. So, it will be 0 to 1000. Okay. Next, let us see the simulation of the LAMMPS file. So, this is your LAMMPS file, previous one was a mole template file. Here important thing is that what we are doing, we are setting up all those parameters over here. First we are specifying the unit, okay, unit is real unit, then bond type is actually hybrid harmonic bond type and angle will be decided by hybrid harmonic. We are also giving the van der Waals and columbic interactions and cutoff potentials over here like this. So, you see for any particles will be having your for LJ potential will be having the lower maximum point and higher maximum point as 9 and 10 and for columbic potential we will be having only 10. Now, for only silicon we will be having there will be no columbic interaction. So, we will be having only LJ potential. So, these will be 9 and 10. Now, using mixed arithmetic we are defining the LJ potential for dissimilar material. We use this type of formulations for epsilon and sigma. So, if you are having two dissimilar material having epsilon and sigma, so epsilon 1 2 can be calculated as geometric mean and sigma 1 2 can be calculated as arithmetic mean. Okay. So, these are given by Lorentz-Breathlow mixing rule. So, this by adding this line mixed arithmetic you can activate these rules. Okay. Then we will be reading the config data which has been generated by mole template using this one, using this line. And finally, we will be setting the LJ potential. So, though we have given LJ potential in mole template file, if you want to change in LAMMPS file, that we can do over here. You see here we have changed for K we have Kr and K theta. Earlier we have chosen 1000, here we have given 200 and 200. Similarly, for different molecules we are having three different types of molecules, hydrogen three different types of atoms, hydrogen, oxygen and silicon. Here we have given 1 as your hydrogen molecule atom, 2 as your oxygen one and 3 as your silicon one. So, you see here we have given all the potentials means epsilons and zeta values over here, okay, for different molecule atom to atom interactions. Okay, next here what we have done, we have created a domain. So, domain is something like this, you see we have created a domain called SI group, silicon group, and we have excluded this silicon group from the whole group. So, we are not considering the movement of the silicon over here. Okay. And then we have given the instruction for running the simulation. So, time step is created as 0.1, and here if temperature increases due to interaction, so for correction we are using thermo after every time 100 time step, and how thermo will be working, that we have given over here using fixed move stuff mobile NVT. So, this is our ensemble actually what we need to take. So, this will be keeping the temperature fixed at 300 at a step of 100 Kelvin. So, 300 Kelvin temperature will be always kept fixed. You can dump the result in some outside file, so that you can see later on using VMD, and you know it will be running for this much time step, okay, and it will be writing a restart file if you are having something problem in between. Next, whatever file you will be writing after the simulation, so you will be actually reading that using VMD. So, this is a typical example of VMD file. So, at the beginning you will be finding out what is the time step, and then you will be having a long data over here. I have shown a shortened one. So, here you will be finding out the item number, then atom type, and then you will be finding out the molecular mass, type, x, y, z, that means x coordinate, y coordinate and z coordinate, and ix, iy and iz. So, those are actually indices for x, y and z. So, here I have shown you one typical example. So, we have started with a water box, and you can find out that at the end of the solution you will be getting a water droplet placed over the silicon. So, this is after 0.2 nanosecond. Okay. So, in this way you can set up one simulation in LAMMPS and you can obtain the result. Okay, let us summarize. So, we have discussed briefly what is the basic theory of molecular dynamics. Installation procedure for molecular dynamics code LAMMPS we have shown, and setting up the simulation also we have shown. In this way we have actually studied a case study of simulation of a nano-sized water droplet over a silicon substrate. We have used mole template, LAMMPS and VMD over here to set up the simulation, perform the simulation and see the results over here. Let us test your understanding at the end of this lecture. So, as usual we are having 3 questions. So, first one, amongst the following which is not valid boundary condition in MD? We have discussed elaborately about the boundary conditions. So, conditions are first one periodic, second one reflective, third one repulsive and fourth one absorbing. Okay. So, most of the names you have heard, so you have to find out the odd one. So, correct answer is absorbing. There is nothing called absorbing boundary in molecular dynamics. Next question, which one is bonded interaction amongst the following choices? So, we are having 4 choices: van der Waals force, stretching force, electrostatic force, all of the above. Okay. Which one is bonded interaction? Okay. So, bonded interaction obviously is stretching force, okay, which is nothing but K R into R minus R naught whole square. Okay. Then in microcanonical ensemble approach, which properties are conserved? So, microcanonical ensemble approach, so that means it is nothing but NVT. So, we have NVE, sorry. So, we are having 3 options: number, volume, energy, number, volume, temperature, number, volume, pressure and number, mass pressure. Okay. So, as it is NVE, so number, volume, energy is the correct answer. So, with this I will be ending this lecture. Thank you.